Okay, so this is the last lecture for EE 597. It's taped, as I mentioned, in my last class earlier today, which means that there is no class on Wednesday again. And again, the exam is on Monday. Okay, during class hours. So, with those announcements out of the way, let's go back and resume what we were talking about, which was intermittently connected mobile networks. And in that lecture, we discussed wait and deliver as the simplest possible scheme. We discussed epidemic flooding and spray and wait. And then we spoke about methods to really analyze ICMN protocols. And I guess the main issue here is that this is fundamentally different from analyzing a standard network protocol because, you know, traditional, let's say static wireless networks, or maybe not so traditional, but static wireless networks, when you have a bunch of nodes, you can really describe them by the graph, right? You can say that these are the nodes, this is who they can talk to, and then on the, you know, edge labels, we might describe what is the ETX of that link. We might look at in the case of back pressure scheduling, we looked at the queue states of the nodes and so on, but somehow the topology itself is more or less fixed. And when you get to mobile networks, already the graph itself might be changing over time, but some of the mobile networks in which the graphs are at least even if they're changing over time, you always have a connected path. The graph might still be meaningful because maybe the graph doesn't change for some period of time and you're looking at what's the shortest path through this network in terms of ETX or whatever metric you care about. But when we talk about ICMN, this doesn't work because there is no moment in time when the graph might be fully connected, and it's not like from, you know, node A to node B, there's a path that you can directly see at that moment is the shortest ETX path. And somehow the way we're describing ICMN, it's not even clear that ETX is a useful metric. Right? For one reason that we really only can focus on, for example, high quality links during the encounter. So we really only care about encounters between pairs of nodes. We say, here's node A, node B, they're within range of each other, and I can define that range however I want. I can define that range to be for all the times that they're physically so close to each other that they're in the connected regime, for example. So there's no impact of fading on the quality of the link. That could be how I choose to define the encounter duration. Or I could simply take the expected, total amount of data that I'm able to send between A and B as they're maybe both mobile and passing by each other for a period of time they're near each other. I can sort of take the sum total of packets that I'm able to send between them, and that's sort of the total amount of content that I can transfer during an encounter, and implicitly we assume encounters are long enough to communicate content between two nodes in an ICMN. And so somehow this assumption is like equivalent to either saying that the encounters are long enough, which is kind of how I described, or equivalently that the the amount of content is low, right? So how much you need to transfer is maybe a few bytes, a few packets. It's not a really large amount of volume of data you're necessarily trying to communicate. I say we make this assumption. We don't always make this assumption. It's just that all of the schemes that I've described so far, when we're describing moving the content, so far our focus has been in this type of a sort of low data rate setting, or imagine, for example, a single item that needs to be moved from source to destination. We're not worried about sort of a overloaded network in the discussion so far. And, you could get into more elaborate schemes if you need multiple encounters in order to be able to download a file. And if we have some time, I might mention and illustrate one of them that we worked on in the past. But generally, the domain we're looking at right now is where the encounter period is just not very long. The amount of data you want to transfer is relatively low. So in this case, if the content is relatively small, the encounter is long enough and good enough, then ETX is not something that we care about. Instead, we care about sort of how do you move the data through the network, how long does it take, and now the latency is dominated not by ETX as a metric. So remember that in a multi-hop static wireless network, ETX has something to do with latency because the number of times you have to retransmit a packet at each link affects the latency. But here, rather, it's dominated by, so in an ICMN, so it's rather dominated by the store and forward. It's really the store time between receiving and forwarding a message. Right? So basically, how long it takes to propagate a message in an intermittently connected mobile network is a function of, I have an encounter now, I get the data, and then the longest time is not how long it took me to get the data, but how long it took me to walk around with the data till I met someone else to hand it over to. So it's as if like the bulk of our latency is not in the transfer of the data, but in holding on to the data till it can be transferred again, right? So given that ETX is not necessarily the metric we care about, shortest ETX path is no longer a relevant notion to focus on. Instead, what we are really interested in is either we have a protocol, we want to see how long it takes, or we know something about the contacts and we want to figure out the lowest latency path or something like that. So we talked about if the mobility is predictable, can construct a trellis representation of all encounters. And we talked about this example. Let's just say I have 3 nodes, 1, 2, and 3, and I have sort of at different times, different nodes meeting each other. So at time 1, 1 meets 2, time 2, 2 meets 3, at time 3, 3 meets 1. I would represent that by a trellis in which the 3 nodes are 1, 2, and 3, and this represents time 1, time 2, time 3 on the pictures above, and on this trellis below, this is time 1, time 2, time 3. And so time 1, 1 and 2 meet each other, we represent by these edges. And time 2, 2 and 3 meet, we represent by these edges. We keep the edges between the same nodes over time just represented that they can store. And finally, 3 and 1 have these edges finally. Right? So this is a directed graph that tells us all the way in which data can be moved between the nodes. So in particular, it tells us that if you had time See, at time 1, data that you wanted to move to to node 3 from node 1, the data could go from 1 to 2 and then 2 to 3. Or a longer way for that data to get would be 1 holds on to it in the first time step, holds on to it during the second time step, and then hands it over in the third time step. So wait and deliver would just do this, right? Whereas if you were doing flooding, 1 would move the data to 2 right away, and then both of them would carry it forward, and then at this time step 2 would send it to 3. So by this time step, all the nodes would have received the message. So basically, whatever protocol you have, you could sort of observe how it would disseminate the data by examining this graph, and you can analyze it if it was for a known schedule in advance. Alternatively, if I had to compute the shortest path, which is not necessarily the wait and deliver path, for example, if I want to move data between 2 and 1 and the data only shows up at time 2, then the best way for me to do that would be to move the data at time 2, move the data from 2 to 3, and then at time 3 move it to 1, right? So this would be the shortest latency way of getting the data from 2 to 1, assuming the data only arrived at time 2. Okay, and so sort of, yeah, time 2 kind of begins or goes back to this layer. Okay. So the only challenge is, do you know all of the contacts and when they're about to happen? And in some cases, for example, if the nodes in question are, I don't know, trains on a schedule or buses, and you have radios on those buses that can communicate with other buses, you know that they will be able to transfer data to each other if they were at the same bus stop at the same time, which if you knew their schedules and if the city was not Los Angeles, you might have a shot at, estimating their locations in advance. Of course, with the randomness in their movement, there's still no guarantee that those encounters will happen. But there may be ways to capture, for example, probabilistic encounters as well by labeling the graphs with probabilities and so on, but we're not going to get into that here. So in any case, this is one approach to try and model the dissemination of information in an ICMN. The other approach, as I mentioned before, is to use the IID encounter model. And this is really a way of handling sort of random encounters. And although the way in which this is modeling encounters is maybe a little too random, there is no correlation over time. By definition, at each time the encounters are completely independent of previous encounters, and they're sort of identically distributed among all encounters. It at least gives a way to start thinking about the performance of different schemes. And so I kind of wanted to show an illustration of this approach, which is for the flooding protocol. So how long does it take to flood a message to all nodes? So let's say we ask this question and see how we would answer that. So in the IID encounter model, we say at each time, pick at random any 2 nodes out of the n choose 2 possible pairs to encounter each other. Okay, that's the IID model. And now we're going to figure out, using this model, how long does flooding take to get the data to all the nodes. So the basic idea is number of infected nodes, if you will, is the state of the network. And, when we say epidemic flooding, that's one analogy we use is like your first node was infected, whoever it met, it infected those nodes, and you're asking how long before everybody gets infected. And of course here an infection is a good thing. We're trying to get this message throughout the network. So the question is, how do we model that infection time? So here's how it might proceed. We said that the expected time to flood, which really is the time it will take you to go from node 1 to all the way, the node marked 1 to the node marked n, where n is the state where everyone has the message, and node 1 is the state where only source has the message, only one source has the message. And we said that this is the expectation of the sum of the times to go from one node having the message to two nodes having the message, from two nodes having the message to three nodes having the message, and so on, all the way up. And so it's this set of times added together. Each of these times are random. So the time it takes to go from just k nodes in the node having the message to k plus 1 nodes having the message is the time it takes for you to pick up two nodes at random where one of them has the message and one of them doesn't. Because if both of them had the message, nothing will move. If neither of them has the message, nothing will move. So this bilinearity of expectation can be written as the summation of E, k goes from 1 to n minus 1, of T, k to k plus 1. And so how to model this expected value is the question, and I concluded the last lecture by saying that we can model this as the expected time to success for a geometric random variable. And what does that variable look like? So let's imagine what's happening at this time. So what's happening at this time is there's a bunch of nodes that got the message. Let's imagine those are these solid filled nodes, and some nodes do not have the message. The experiment that I'm doing at this time when k of them, right, k nodes have message, and n minus k do not. But what I'm doing in the mobility model or the encounter model is I'm taking two of these at random and making them meet each other. I might pick these two nodes to meet each other. Nothing will happen in that case because they both have the message. I could pick these two nodes and nothing will happen because they both don't have the message. Or I might pick these two and then the message will propagate, and that's when I'll go from state k to k plus 1. Right? So the probability that I will have a success in going from k to k plus 1 is the probability that in the pair I pick, one of them is marked having the message and one of them is marked not having the message. Okay? So the probability of success equals probability of picking one node with data and one without. So the probability that you pick a node that has the data is, and one without, is k times n minus k. Okay? These are all the combinations of pairs in which one of them has the data and one of them doesn't, divided by all the possible ways in which you could have picked two nodes, which is n choose 2. Right? So that's the probability of going from k to k plus 1 in one time step, where I have k infected nodes and n minus k non-infected nodes. So n choose 2 is n, so k times n minus k. What is n choose 2? That's just n times n minus 1 divided by 2. Actually, I'm wondering about this divided by 2, given that I did this as k. think about this for a second. So I have some confusion here, because if you look at the number of ways in which we could have chosen the I think there was a factor of 2 here also. So why do I not see that? Looks okay. All right. So let's go with this. I might have a factor of 2 off, but I'm not seeing it off the top of my head here. So so this is our probability, success probability in one time step that we are picking one infected and one non-infected node. And the time to go from k to k plus 1 is simply 1 over p k to k plus 1, because this is a geometric process. Each time with this probability I have that event happen, I'm asking how long till that event happens. So that would be equal to 1 over this. Let me leave it as n choose 2. We'll see it's going to factor out, I think. N choose 2 over k times n minus k. And going back to the total flooding time that we want to find the expectation of, this is the expected time to go. So the total flooding time is going to be simply the sum of these quantities going from 1 to n minus 1. So n choose 2 over k times n minus k. So I can write this as n choose 2. Summation k goes from 1 to n minus 1, 1 over k times n minus k. So it's not immediately obvious how to calculate the summation, but there's a algebraic substitution that will help us. And the way to see that is to consider something of this type. So if you say I want to add up these two numbers, I would end up with n minus k plus k over k times n minus k. Right? So in other words, the sum of these two numbers equals n over k times n minus k. In other words, if I take that n down here, 1 over n times 1 over k plus 1 over n minus k equals 1 over k times, 1 over k times n minus k, which is exactly what we have here. So we can substitute for this expression down here, and we would get n, so the expected flooding time would become n choose 2 summation 1 over n, 1 over k plus 1 over n minus k. This term on the outside of it, the product, has actually nothing to do with the summation. It has no k in it. We can pull it out. So we get n choose 2, which is n times n minus 1 over 2. We have this n over here, so it'll cancel this n. And then we're left with a summation of k goes from 1 to n minus 1 of 1 over k plus 1 over n minus k. And we can rewrite this as n minus 1 over 2 times the summation of k goes from 1 to n minus 1 of 1 over k plus k goes from 1 to n minus 1 of 1 over n minus k. So if you look at this summation, the first term is going to be n minus 1, and then it'll go n minus 2, n minus 3, n minus 4, all the way up to n minus 1, which is just 1 over 1, right? So this is all the terms like 1 over n minus 1 plus 1 over n minus 2, dot, 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 1 over 1. This is all the terms 1 over 1 plus 1 over 2 plus dot, 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 1 over n minus 1. And you can see that these two are basically the same term, right? And so, in fact, they cancel each other out. You're just left with 2 times one of these, and that 2 cancels with this 2, so you're left with n minus 1 over 2 times 2 summation 1 over k. K goes from 1 to n minus 1. And this summation doesn't have a closed form, but it's sometimes called the harmonic series. And roughly speaking, and there's a constant associated with it, it's like log n plus a constant. Okay, so it grows, as n gets larger, it grows as log n plus some constant, roughly. And so this whole solution that you get, the expected flooding time, ends up being something that's, in big O notation, like n log n. Okay, this is called big O notation if you've seen it in computer science. But roughly speaking, it's like saying in order it grows as n times log n. So what is this saying, n times log n? It's saying that the total number of time steps that it takes to propagate the message throughout the whole network is growing as you add more and more nodes to the network, as n times this log n term. And this is under the assumption that at each time we're only allowing one pair of nodes to encounter each other at a time. So under that model, we're able to kind of describe how the flooding would grow. Now in practice, if you have a network and you grow the number of nodes in that network, you would expect that the time between encounters would actually shrink. Because in practice, so this is total number of encounters, okay? So if you say, what is the unit of this flooding time? It's how many encounters does it take? But in practice, the number of encounters per unit time will increase with the number of nodes. Okay. Example, if, well, I don't know what's a simple way to see this, but one intuition you might have is that there's sort of a constant rate with which each node might meet some other node. And so if you're increasing the number of nodes total as n, the number of pairs of nodes is increasing as n squared. And so if each pair has a constant rate of encounter, then number of encounters grows as order n squared. Okay? If this is true, why would this be true? For example, fixed area. So just to put this in context, imagine at USC we introduce an app that allows two people carrying their phones to send a message to each other if they're close to each other. So I first introduce this app, maybe 20 students sign up for it, right? Maybe a month later, 200 students have signed up. A month later, maybe 2,000 students signed up. Maybe a few months later, the entire campus full of students has this app installed, right? As we increase the number of students carrying this app, that's the n in our system, the area over which they are present is not changing. So on average, how long it takes for a pair of them to encounter each other, if you say that that's a constant, then the number of pairs would be growing with the network deployment as n squared, right? And so the number of times that you will see encounters will grow quadratically with the number of users of the app, because the area has kind of fixed to be the USC campus. So if we make this type of an assumption, then the time to flood will scale as number of encounters times seconds per encounter. And what I'm saying is that the encounters per second is growing as order n squared. The number of encounters to flood, which we computed is order n log n, will basically grow roughly as n log n times 1 over n squared, or in other words, as proportional to log n over n. Okay? And what's interesting here is that as n gets larger, or as n tends to infinity, the expected time to flood would tend towards 0. Or at least that's exaggerating, because n can never be quite infinity. You know, even in a campus, we're not going to get infinitely many students. But if you have a large number of students, it's telling us that the infection will be a lot quicker. In fact, everybody will get the data. When there's enough users in my system, they'll get the data very quickly indeed. Okay? So it's saying flooding time decreases with population size here, but in a fixed area. Okay? The in a fixed area is important for this 1 over n squared assumption. If you assume that you're acquiring new users by growing your area, so for example, if I have an app I introduced originally to Los Angeles, I get a certain number of users, the number of users in LA doesn't really change, I then go, get some more users in Santa Monica, then I get some more users in Malibu, then I get some more users in West Hollywood, and so on. Then as I'm adding the size of the network, I'm also growing the area. And in that case, I wouldn't necessarily expect the number of encounters to grow with the number of pairwise number of users. It might actually stay, even just the rate of encounter may not even change. It may just remain a constant. So in that case, actually, my total time to flood the entire network will grow with the size of the network, which kind of makes sense because then I'm increasing the area of deployment. But if I'm keeping the area of deployment the same but increasing the number of users, this is telling me that I might expect to see my data getting to users quicker, which is a little counterintuitive because I have a bigger network, but now things are happening quicker. So it's telling you that you can leverage that density in these systems. You have to take the analysis a little bit with a pinch of salt when you let n go to infinity and keep the area fixed, because at some point the network is going to just become a connected network. You don't even need to use flooding through an intermittently connected mobile network model to disseminate the data, and they will more or less be able to just flood the data like a multi-hop wireless network rather than wait for encounters to happen. But at least it gives you some intuitions about how systems might behave at scale. So the key idea here was just take a stochastic model of mobility, run your protocol over the stochastic model, and then what can you say about performance? All right, so that's really all we have to say about the network layer. There's been a lot to say, but hopefully you get an idea that there's many different types of multi-hop wireless networks. They demand different solutions, and really we're still in the very early stages of developing multi-hop wireless networks. A lot of these protocols and mechanisms are still being developed and analyzed as we speak. So I want to move on to the last layer we'll get to talk about in this class, which is the transport layer. And I just want to spend 10-15 minutes talking about, is TCP good enough? And before I go there, let me just acknowledge that if we're going to use UDP, there's going to be no change needed, because UDP doesn't, to begin with, guarantee much. right? UDP just says, I'm going to best effort get your data through the network to the final destination. You have IP addresses, you have a routing protocol, whatever that routing protocol might be. I'll do my best to get your data from source to end. I'll give you ports to multiplex your applications, but that's all I provide. If you're going to use UDP, whether it's a wired network or wireless network, there's no fundamental change that's required, and at least in the research literature, for that reason, UDP has not received much attention. TCP, on the other hand, has received attention, and it's received this attention for two different reasons. Okay, and one has to do with the rate control over dynamic quality links. And somehow, in wired networks where TCP was first invented, you don't really expect the link on a particular pair of nodes, the link between them, to go up and down over time dramatically, like to be really dynamic. And most of the time, you don't even lose packets on wired links. I mean, occasionally a whole link might go down for a long period of time, but you don't see sort of short-term probabilistic reception of packets. It's not like 40% of packets get through a wired link. Most of the time, the packets are getting through. So something about, that you encounter in wireless, these probabilistic packet drops turn out to have a big impact on TCP performance if you just take the simplest possible scenario. So let's just take a source and a destination that are simply separated by a single hop. Okay, and I have the source sending data through a TCP stack, and then at the receiver end, of course, I have TCP delivering it to my receiver. So what ends up happening? Note that in traditional TCP, you're doing congestion control. You do additive increase, multiplicative decrease. Of the congestion window, or some people directly, look at it from the lens of rate, like your data rate increases linearly. When you see losses occur, then you cut back. So the decrease is triggered by timeouts due to packet loss. So the packet timeouts when awaiting an ACK. Okay, so TCP sends a packet, the packet gets lost. It assumes that the loss of the packet is because of congestion, doesn't get an ACK back, and then decides to cut back the data rate. Right. So if you've all seen the sawtooth figure we talk about with TCP, the cutting back part of it is entirely because of loss events, right? In a traditional wired network, that's fine because all of your losses are due to congestion, right? So this is fine if losses are primarily due to congestion. What is congestion? Congestion means that you have a router somewhere in the interior of your network that filled up, its buffer filled up, it's unable to process packets fast enough. And in this situation, the right thing for sources to do is to stop sending packets so that that intermediate buffer that's congested can get a break, can service the packets that it has, and then decongest the network. Now you can try to increase your rate again. That's why you increase the rate again sort of slowly. But if your loss is primarily, in this example, on a wireless link, there is no example, there is no place in the network where congestion can occur because the source is simply, forwarding what packets it has. The destination is getting that packet and sending it up. There's no intermediate router really. So if you're seeing packet losses in this system, it's not because some router buffer is overflowing. You're seeing losses because the link itself is acting flaky because of fading. Okay, so when we say the PRR is some percentage, maybe the PRR here is 30%, 20%, 20% of the packets go through, 80% of the packets get lost. What will happen to TCP under such an environment is every time the packet is lost, it's going to cut back its rate. And because packet losses happen 40% of the time, 60% of the time, 80% of the time, you're constantly cutting back on your rate. And even though there is no place where there's congestion happening, and cutting back on rate doesn't solve this problem. Like your link loss is independent of the rate at which you send packets. But traditionally, the problem for which TCP was designed was to handle the fact that your packets are getting dropped due to congestion, and that could be solved by reducing the rate. So in a wireless network, on a wireless link, let's say, the losses due to fading are not affected by send rate, and if treated the same as congestion, will result in very low throughput. Right? So in fact, what you want to do is you want to separate losses because of link failure from losses due to buffer overflows. So need to which is what is called congestion. So congestion control should only be applied when congestion happens. It shouldn't be applied when packet losses happen. Because there's nothing about reducing your data rate that's going to improve packet losses due to fading. And as a result of this observation, any implementations of TCP that go over wireless links are typically enhanced with the use of something called explicit congestion notification. The basic idea is that intermediate routers mark packets when congested. Okay? So source can then differentiate congestion from channel loss and only respond and only cut data rate due to congestion events. Okay. So now it won't do the sawtooth behavior by scaling back its data rate if the loss is not explicitly because of congestion, which it will now know because congestion events will be signaled by the routers whose buffers are overflowing. So just because a packet's dropped doesn't mean you assume it's congestion. You assume it's congestion if the router tells you it's congested. So this is a solution that's being used in multi-hop wireless networks in many settings. Of course, it does require that every router be capable of recognizing that it's congested and be capable of marking packets as they're going through it. So long as you have this router-centric capability in your network, you can implement the solution. If you don't have that solution, you're probably going to see a very low throughput wireless network, and that's actually something that deployments where they're unable to change the intermediate routers will suffer if it's a multi-hop wireless network. The second challenge is a problem of fairness and flow starvation, which is the opposite of fairness, if you will. That can occur for, we call them sort of flows in the middle. So give you a concrete example. Let's look at maybe 3 different flows. So here's flow 1, here's flow 2, and here's flow 3. All three flows, let's assume, are TCP flows, so they're all choosing their data rates based on the current available bandwidth as signaled to them by observing congestion in the network, and they will either increase or decrease their data rates depending on what signals they're getting from the network. So what happens in this system if you employ a TCP is that flow 2, and in particular this router, relay router, sees the most interference, okay, and hence has the lowest capacity among the relays that the three relays that you have. Okay, so this router over here, which sees the most interference from these two nodes, it's periodically, as its data rate keeps increasing, because of that interference, it will be kind of taking longer. It will see collision events, or it will see that the channel is busy if it's a CSMA-based router, and so it will pick a longer back-off window to send the next message, and so on. And so it's going to fundamentally see a lower data rate, lowest capacity, due to higher back-offs when using CSMA. So the assumption I'm making here is that, say, this router can only see this node, this router can only see this node, but the intermediate router can see both of them. So if either of them is sending a packet, it has to wait and then, pick a random time to transfer, whereas these guys only have one potential node who might be occupying the channel when they want to transmit. So as a result of this, and it has the lowest capacity, tends to cut back its rate more often. And whenever it cuts back its rate, it sends a little bit, less frequently. Then what's going to happen on this flow is that this flow will observe when this one has cut back its rate down to 0 and, is working half the rate and working its way back up. Suddenly this node will notice, hey, wait a second, there's actually a lot more available resource here. I'm able to send my data pretty quickly. The flow here with its sender, it's going to increase its sending rate, which will cause this intermediate router to become more congested, right? So causing outer flows to increase their rates, in turn causing more congestion for the middle flow. Okay, and basically this escalates until F2 has close to 0 rate. And people have observed this in real experiments. What you can do is you can take 1, 2, 3, 9 different wireless devices, put 3 of them kind of in a topology like this, where these two nodes are close to each other, these two nodes are close to each other, but these two are far from each other, and run TCP on each of the sources over here, and measure for a period of time how much data rate each flow is getting. And what you observe over time, maybe initially all 3 flows start with the same values, but that flow in the middle slowly starts to decrease, and the other 2 flows start to increase their rate. And after some time, basically you find that flow 2 and 3, kind of stabilize at rates roughly equal to each other, and flow 2 basically crashes and ends up getting starved. Okay. And this is something that you can empirically observe. You run TCP and you'll observe this time and again. And other more complicated topologies, the similar type of phenomena will happen. It may get a little bit trickier to see which flow is being affected more than others, but as a rule of thumb, the flows that see the most interference basically go down to 0, and flows that see less interference can grab all of the remaining bandwidth. So they play very poorly with each other if they're using TCP. And in the long run, so in the short term, this is bad for flow F2. On the other hand, while F2 is starved, okay, F1 and F3 get more capacity than they would have, right? Because F2 is down, then these two flows, the outer flows, will see no interference with each other, so their data rates will be very, very high. So in fact, they'll finish even quicker than if all of them were transmitting at the same rate, okay? And can finish quicker, assuming they're finite flows. They have a fixed amount of time that they need to run, at which point allowing flow 2 to then start later, okay, and finish. So, although in the short term this is bad for flow 2, in the long run, total time to complete all flows might actually be shorter. With TCP in wireless setting. But not always of interest. Okay? So this is an interesting fact that even though you do starve this flow, eventually when these two flows finish, they will be done, and then this flow can then grab all of the capacity that's available, and maybe it can finish. And if you look at the total amount of time, depending on how long the files were, let's say that they were all sending, the total amount of time taken to complete all of the file downloads might be quicker in the setting, but if you look at certain moments in time, there's the flow that's simply not getting any data rate in the network, and generally that's not considered a desirable feature of a network. And so, because of this fairness issue, people have proposed various solutions, and I won't get into the detailed solutions if nothing else because we're running out of time, but the key idea is so flow 2 suffers congestion from flow 1 and 3, but only F2 cuts back its rate. Right? So the intuition is if F1 and F3 could both also cut back when F2 cuts back, it would improve fairness. So this was the intuition, and there are a number of papers, one of which is called WCP, which is a paper by faculty also at USC, Sunis and Govindan, that kind of implements this idea. So going back to this picture, what it does is that when F2 notices that there's congestion because of interference at this router, it marks the packets going through this router explicitly as having congestion, but it also signals other nearby routers to also start marking their packets. So in this case, this router and this router, both are also marked as being congested, even though they are not themselves congested, but one of the routers in their neighborhood is congested, and so they signal back to their sources that they should all cut back the rate. And so now when congestion happens, instead of just this F2 going down, all of them will go down a little bit, and that basically allows them to recover fairness. So if I can maybe find, I don't think this will work. One thing I will do is we'll post some pointers to papers addressing TCP fairness, that you might want to browse and understand this issue. But really the takeaway lesson is the following. The network layer, we had to completely rethink how to design the wireless systems. And at the transport layer, you don't have to rethink what you do for UDP because it's best effort anyway. And there's no responsiveness to either loss or to congestion. And so there's nothing you can really do differently in a wireless setting than a wired setting. However, for TCP, which is the more intelligent of the two transport protocols, trying to ensure reliability, trying to ensure that it doesn't overload the network when it's congested, then you have these two sets of issues to deal with. The first is the problem of what's called loss differentiation. So the first problem is the problem of loss differentiation, and that's solved using explicit congestion notification packets. And then the second problem is the problem of fairness, or at least short-term fairness, and that is solved using shared congestion notification, where the idea is that routers that are congested share the fact that they're congested with other nearby routers who must also mark using ECN packets. So somehow this use of ECN packets in a multi-hop wireless network is a distinguishing feature. And in the future, as people are developing more multi-hop wireless networks, you're going to see either variants of TCP or completely different alternatives to TCP really emerge as a standard, and this is still work in progress. For example, in the low-power wireless sensor networks field, there really aren't any good implementations of reliable transport yet. That's an open problem that people are still looking at. So we're going to stop here. And there is no class again on Wednesday, and we will meet on next Monday in class for the final exam. Thank you.